This is lecture 11 of Physics 210A, that is thermal physics. And in today's lecture, I'll first be combining the first law of thermodynamics and the second law of thermodynamics to obtain something called the central equation of thermodynamics, or the thermodynamic identity. And then we'll go on to discuss thermodynamic potentials and why they are needed. And today's focus is going to be on the internal energy and enthalpy. And using those potentials, we'll also be getting what are known as Maxwell's relations. So to begin with, let's combine the first and second laws of thermodynamics. Now, first law says that if you undergo a process, then dq is equal to du plus dw. dw is also path dependent. So if you have two nearby points infinitesimal apart, although u and u plus delta u depend only on these points, the work done and the corresponding heat depends on the path as well as whether the process is irreversible or reversible. So let's write this, that between point 1 and 2, the delta u between points 1 and 2 depend only on these endpoints. The work done and the heat exchange depend on the path as well as whether the process connecting 1 and 2 is reversible or irreversible. Now imagine if I could write this difference only in terms of quantities that depend on points 1 and 2. I'll have a relationship that depends only on those points. So to begin with, if the process is reversible, then I have dq equals t ds. And the work done is p dv, or if you have some other variables of the system in terms of that, whatever it is. And if you do that, what you get is t ds equals du plus p dv. Just to write in terms of delta, let me just write this as t delta s equals delta u plus p delta v, where all these delta terms are infinitesimal. I'm writing this as delta to facilitate making this on a process and end of the process. So consider a process infinitesimal apart between 1 and 2. At 1, I have the internal energy U, entropy S, volume V. And at 2, I have internal energy U plus delta U, entropy S plus delta S, and volume V plus delta V. And all these delta U, delta S, delta V depend only on point 1 and 2. Delta U, delta S, and delta V depend only on points 1 and 2. And therefore, if I write the equation T delta S, so I've removed delta Q, instead I'm writing T delta S equals delta U plus P delta V. This equation is true irrespective of how the 2 points 1 and 2 are connected. Why? Because delta S, delta U, and delta V depend only on points 1 and 2. So this is true irrespective of the process. It depends only on the endpoints. So this is known as the central equation of thermodynamics, and written as T ds equals du plus P dV, or also known as thermodynamic identity. So it's a thermodynamic identity, true irrespective of how we are connecting the 2 points. Because you see these all the quantities given here are defined irrespective of the path. The changes are irrespective of the path. So this is the combining first and second law to obtain an equation relating infinitesimal changes between 2 states close by. Close by means they are separated by just infinitesimal amount. So this is the central equation of thermodynamics. Now using this, we are going to obtain different thermodynamic potentials and Maxwell's relations. So let me first motivate why we need different thermodynamic potentials. Obviously, when we say these are potentials, they have the capacity to do some work. So to start with, let's look at internal energy. So from the central equation, we have du equals T ds minus P dV. So the differential, total differential of U is related to the differentials of S and V, and therefore I'm actually considering U as a function of S and V. Now, you see, when I write du in such a way, then in considering u, we can look at thermodynamic processes where ds is 0 or s equals constant, or dv is 0, which is isochoric process. But not necessarily all the processes are like this. So, we need to define other quantities where we can take, for example, we could have p constant. What kind of quantity should we have then? So, let me just ask you a question here, and the question is, what kind of process does s equals constant or ds equals 0? Indicate. Give reasons for your answer. So, for example, if I now consider a process where p is a constant, if we consider a process where P, the pressure is constant, we need a quantity different from U for this. Now, again, let me ask you a question here. I want you to recall that we have already encountered such a quantity earlier, which quantity is it? Well, of course, later in the lecture you will see what this quantity is, but I want you to think at this point as to what quantity are we talking about. Now, let's go back to the central equation where I have du equals T ds minus P dV. From this, if I take this to be du over ds T dt plus du over dV at constant s dV, then you can immediately see that we have change in the internal energy, partial change in the internal energy with respect to the entropy at constant temperature equals the temperature. Oh, sorry, this is at constant V. There's a mistake. So, this is at constant V. If I keep the volume the same, change the entropy, then the partial change of U with respect to S is T. And similarly, partial U over partial V at constant S, that is, no heat is being exchanged, is equal to minus p. Again, I'd like you to discuss the physical meaning of these equations. So, we have just obtained partial derivative of u with respect to the entropy at constant volume is equal to T, and partial of u with respect to V at constant S is equal to minus P. Now, this leads to something called the Maxwell's relation. One of the Maxwell's relations. And what does that do? To obtain that, notice that u is a state function. Du is a perfect differential. It does not matter which direction you are coming from, the change in u is path independent. And therefore, from the equation where we have partial u over partial s at constant v equals t and partial u with respect to v at constant s is equal to minus p, I can also write, because du is a perfect differential, I can write partial v keeping s constant, partial u over partial v, partial u over partial s at constant v. So, I am switching the order, is equal to partial derivative with respect to s at constant v times partial u over partial v at s. And this gives me that partial derivative of temperature with respect to v at constant s is equal to minus partial derivative of pressure with respect to entropy at constant v. And this is known as the one of the Maxwell's relations. It relates the change in the temperature with respect to the volume if entropy is kept constant to the change in pressure with respect to entropy if volume is kept constant. And these can be used very effectively in carrying out thermodynamic manipulations, calculations and manipulations. Now, using u, we will also use, and the central equation we will also express Cv in terms of u and s. Now, for a reversible process at constant volume, we have delta Q equals T delta S. So, Cv, which is partial Q with respect to partial T at constant volume, is equal to T partial S with respect to partial T at constant volume. And since volume is constant, the first term is also du dt at V. So, we have gotten two expressions for CV. So, CV is du dt V, or it is also equal to T partial S partial T with respect to V. And let me box this. So, this is playing around with internal energy. Now, let us take another quantity which I talked about earlier, which will be useful when the pressure is constant. So, before that, let me just write that internal energy became useful when delta V is equal to 0, because then dq is equal to du. What about some other processes? What if delta P is equal to 0, or some other delta P delta T is 0? In that case, we define different. So, in this case, in such cases, we define different, again, state functions known as thermodynamic potentials and get their meaning. So, next quantity that I am going to consider in this regard is the enthalpy, and you have already come across this. This was in connection with throttling process, which was isenthalpic. So, I would like you to go back and see this. So, enthalpy is defined as H equals U plus PV. It is also a state function. Depends on the state, no path business. So, you have dH is equal to du plus pdV plus V dP. And I can write du as T ds minus P dV using the central equation, and then I add P dV plus V dP. These terms cancel and you get T ds plus V dP. So, for enthalpy, H, I have dH, which is du plus pdV plus V dP, which comes out to be T ds plus V dP. Again a comment. this relation also gives the difference between state functions. Which are infinitesimally closed states. So, this is also true for reversible or irreversible process. Note that if I wrote TdS as dq, that will be true only for reversible process. So, just a note, if we wrote TdS equals dq, then dH equals dq plus VdP will be true only for reversible process. So, in this case, since dH is equal to T ds plus V dP, H is a function of S and P. And it is easily seen that dH ds at constant pressure is equal to the temperature, and partial H with respect to P at constant entropy is equal to the volume. So, what we found is, we call it thermodynamic potential H, entropy, enthalpy, for which the central kind of equation is dH equals T ds plus V dP, and dH over ds at constant P is equal to T, and dH over dP at constant S is equal to V. And from this, we obtain the Maxwell relation. Another Maxwell's relation, and that will be by taking the derivative of T with respect to P at constant S, which will be equal to derivative of volume with respect to entropy at constant P. Let me box this one also. So, this is another Maxwell relation. Usefulness of these relationships, I'll keep giving you examples for that. Now, let's define the constant. As I said, enthalpy comes in handy when we talked about constant pressure processes. So, now we will use this to define Cp, that is specific heat at constant pressure. Now, Cp is equal to partial derivative of Q with respect to T at constant pressure for a reversible process. And for a reversible process, Q is TdS. So I can write this as dQ is TdS. So this is ds over dt at constant pressure. And you can also see this is equal to dH over dt at constant pressure. So this is similar to how we define Cv in terms of du dt at constant volume and T ds dt at constant volume. Now here for the pressure, the enthalpy becomes the quantity of choice. Now I'll give you an example of application of Maxwell's relation. So for that, I'd like you to do something before that. That is, use Maxwell's relation dt dp at constant S equals dV d at a constant P to obtain dV dt at constant P equals minus ds dP at constant T. This is another Maxwell relation, which of course I'll obtain through another thermodynamic potential later. But right now, what I want you to do is use the relationship derived earlier, partial x partial y, z partial y partial z x partial z partial x y equals minus 1. So I'd like you to obtain this, and I'm now going to use this to solve a problem. As I said earlier, later using a different thermodynamic potential, I'll get this relationship also. So the problem I'm going to solve is calculate the heat given out by a block of metal when it is compressed reversibly and isothermally from pressure Pi to pressure Pf. Since it's being compressed, Pf obviously is larger than Pi. It is obvious that Pf is larger than Pi. So, for a reversible process, we have dq equals T ds. And what we are doing right now is keeping T constant and changing P. So, I can write this as T partial S with respect to P at constant T delta P or dP. So, the heat I am calculating is dq equals T partial S partial P keeping T constant dP. Now, I am going to use the relationship derived earlier and say that this is T times minus dV dt at partial p times dp. Now, dV dt can be related to a physical quantity. I know that the volume expansion coefficient beta is 1 over v dV dt at constant p. And therefore, I have dq equals minus T v beta dp. Now, assuming that during the compression the volume V does not change much, we get delta Q equals minus T V beta dP integral, which will be minus T V beta P final minus P initial. Since there is a negative sign, Pf is greater than Pi, so this much heat is released by the block. Problem solved. So, you see the usefulness of relating different quantities and their derivatives through Maxwell's relations. So, with this, I will conclude today's lecture. So, what we have done today is the thermodynamic identity, which is central equation of thermodynamics, has been obtained. To Maxwell relation based on U has been derived, and also CV has been defined in terms of U and also in terms of S. And finally, Maxwell relation based on enthalpy has been derived, and Cp has been defined in terms of H and also in terms of S. Thank you.